Hi friends, I am Srirak. Okay, this is my first video. If you like this video, please subscribe it. Okay, today we are discussing about what is critical radius and how can you find, can you derive an equation for this critical radius. Let's consider a cylindrical pipe. Okay, imagine you are covering the outer portion of this cylindrical pipe using thermal insulator having a thermal conductivity K insulator. Okay. And the inside radius is R1 and the outside radius is R2 and the radius of this insulator is RC, BRC. Okay. Okay. If we are increasing the radius to a certain limit, the heat transfer rate will also increase. You can see it from this graph. Okay. For a certain limit of R. After that, the heat transfer rate get decreased. Okay, that means at this point the slope of this curve is 0 and it has the maximum heat transfer rate. This radius, this radius of the insulator at which the heat transfer rate is maximum, this radius is known as the critical radius, RC. Okay, then how can you derive it? We all know this simple relation, heat transfer rate is inversely proportional to the resistance offered by this body. That means the cylindrical pipe here. Okay, and proportional to the temperature difference. Okay, again we have to go for the graph. I already said that the slope will be 0 at this point. Okay, so for getting this critical radius, we have to find this. We have to use the condition that the slope at this point is 0. So we have to differentiate this curve. This curve. That means the relation between Q and R. So you can assume that the slope is 0 at this critical radius. Okay. That means at critical radius we have dq by dr is equal to 0. And we are considering here a spherical, not spherical, sorry, it's a cylindrical pipe. So we have, we are aware about the resistance offered by this cylindrical pipe. R is equal to some simple formula, basic formula of conductivity resistance offered by the cylindrical pipe. Okay, so in order to get the maximum value of Q, the resistance offered will be minimum. That means we can also use the minimum value, of this resistance offered. So instead of using dq by dr, can also use dr by dr. That means it equals 0. That means at this condition, the radius, this is not radius, the resistance offered by the cylindrical pipe will be maximum. Sorry, minimum. So heat transfer rate get maximized. Okay. So we can use this formula instead of this. Okay. Then just differentiate the resistance. Okay. and take 1 by 2 pi L as constant. That's take it outside, and the first two terms are constants. Okay, again then the derivative of these two terms will be 0. Okay, and the derivative of third term, that means 1 by k instead is the constant, you take it outside, and sorry, the 1 k instead takes it outside, and the only variable is r. Okay, you can simply differentiate this term and obtain 1 by k instead to r by 2 to r by 1 by r2 plus and 1 by HO, yeah, thermal convexity coefficient outside this pipe, that's HO. It's a constant, you can take it outside and differentiate 1 by R. That means minus 1 by HO into 1 by R square. And the whole term is 0. 1 by 2 pi L will not be 0. So the term inside this bracket is 0. Okay, from this we can obtain 1 by k integration into 1 by r is equal to 1 by h0 into 1 by r square. Just replacing this term to right side. Okay, then just put this r square term to the left side, and you can simplify it into r is equal to, so that means the critical radius, condition for critical radius, rc is equal to k insulation by h0 HO. Okay, this is our derivation. This is our final result. Okay, we have to check whether it is dimensionally correct. We know the radius of the radius, it has a dimension unit meter, and the thermal conductivity watts per meter Kelvin, and convectivity watts per meter Kelvin, and the ratio of these two terms will give a unit of meter. That means it's dimensionally verified. Okay. This is the formula we have obtained for critical radius. Thank you.